good? Sweetness. Okay, we are going to do our common logarithmic parent function, and it looks like y equals the log of x. And even though you can't see it, this is the one with the base 10 down here. It's understood to be base 10. It will not write it. If it says the word log, it's understood to be base 10. Okay? It says natural log, it's understood to be base e. We are dealing with common log, so make sure you're on the right page before you fill this out. Okay? All right. Just to give you a refresher, if we were to write it as log base 10 of x equals y, and we did lean to the left, lean to the right, equals the middle, get it right, okay? Mm-hmm. If y were to equal 0, what would x be?
1.
1. Okay, so x, y, 1, 0. Okay, that is going to be your huge point on your graph. Okay, is that kind of making sense? Even though your graph is actually on one scale is labeled by 1s, this is by 2s. I wish it was by 1s, but the reason we did it by 2s is for the next number you're going to see. And let me just show you that. If we had 10 to the first, what would the number equal? 10. 10 to the first is 10, correct? So when x is 10, what is y?
10. Or 1.
1. So those are the two main points that you're looking at.
Okay.
Okay? You can always tell what base your log is because the y will equal 1 at that point. So way over here at 10, this is going to be up at 1. Are you seeing that?
Mm-hmm.
Yes?
Yes.
Okay, so it's going to look like this. Okay?
Mm-hmm.
But it doesn't get 1, 0, so in here it goes to 0. Okay? So, sorry my graph looked bad, but I just kind of wanted to give you an idea of the log business. Okay, remember logs are exponents, and that's basically what you're graphing here. Alright? And I'm sure my little deal here isn't perfect, but it just basically stops. Okay?
Mm-hmm.
Okay. If you look at domain, domain is when you're looking at your graph from left to right and you want to know what works and what doesn't work. It's bigger than 0. X is an element of the reals. Okay? Sorry. Range. It doesn't look right, but it's y is an element of the reals. And if we looked on your calculator, the graph's going to look better than what I have right now. And you can see, however small this number is, this is going to be a much smaller exponent. Okay?
Mm-hmm.
If you zoom in real close, do really small scales, you can see how it just darts down. Okay? It will never cross. It will never cross the y-axis, so the y-intercept is none. And one way you can do that is if you were to plug this in, you would end up getting undefined, where x is equal to 0.
Mm-hmm.
Okay? Your x-intercept?
1, 0.
Correct. All right. Are you doing okay there?
Mm-hmm.
On symmetry,
None.
this one has none. Okay, did that make sense when you graphed it? Does it look better on your calculator? Is that what you were doing?
I was trying to do that.
Okay, I'll help you with that shortly. Asymptotes. This one does have an asymptote at x equals 0. Okay, this number can never be 0. Because I can't raise 10 to some power and make it be 0. I can get really, really close,
Mm-hmm.
but I can't make it 0.
I didn't know the asymptotes were allowed to cross the function.
They don't. This one just keeps, this one goes this way.
Oh, okay. Good point.
This one goes this way.
Okay.
You can cross a horizontal asymptote, you cannot cross a vertical asymptote. Or
Okay.
a graph won't cross a vertical asymptote. You can jump it, like it did on that hyperbola, that linear inverse. Okay. All right. We did asymptotes. Okay, so we need to talk intervals of increase, decrease. Okay, so if we've got negative infinity here, we got 0 here, we got infinity here. What's happening as I move from 0 across? What's going on with the graph? It is
Increasing.
increasing. So under intervals for increase, we would say our interval is from 0 to positive infinity. For interval of decrease, we would say none. For relative maximum, there is none. For a relative minimum, none. Intervals of concavity. So I'm going to use the same little graph thing here, only we're going to talk about concave. This is actually considered concave down. Okay?
And that would be as it's going to infinity.
So concave up, there would be none. There are no places where this is concave up, but concave down is going to be from 0 to positive infinity. All right? There are no points of inflection. It goes from having no part of the graph at all just to being concave down. That's not a change in concavity. All right? As x approaches negative infinity, what's happening to y here?
There's no y.
So it's
None.
non-applicable. Okay. As x approaches a positive infinity, what is happening to my y?
Y is approaching infinity.
That is correct. Y is approaching infinity. All right. I'm going to give you the alternate forms. It's going to be y equals a times log, and I'm not going to put the 10 in there because it's understood, x minus h, close parenthesis, and then plus k. All right? And again, the h moves it left and right, k moves it up and down. A is a multiplier, whether it goes fast or slow or opens up or down kind of thing. Okay? Locator points. Well, for your regular one, for your regular common log, you basically have two locator points. One is the 1, 0, which is your x-intercept. Okay? The other point, your other locator point, is at 10, 1. And the one that has the 1 and the y is good because it always lets you know what your base is.
And then
Okay.
another one is HK, right?
Well, almost.
What do you mean almost?
Almost. It's actually, if you're looking at this one right here, it's going to be h plus 1,
Ah.
comma k. And h plus 10, comma k plus 1. So it's basically these two things, only you add hk. Are you okay with that?
Yeah.
The other thing that you would need to know is that this puppy up here had an asymptote of what? X equals 0?
Yes.
So
you
down
need to write
here,
that.
your asymptote isn't going to be at x equals 0, it's going to be at x equals h. Are we good to go on that one? Sweet. Okay, now we're going to head over to